Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this is some work that I'm going to, some work with Pratik, whom you all know, and Pravesh, who was our intern in summer 2013. So please ask questions whenever something is unclear. So this talk is going to be about two fundamental entities. So submodular functions, which are some sort of discrete analog of both concave and convex functions, and I'll tell you more about them. And in particular, I'll be interested in submodular function minimization and projection algorithms. So given a body in some n-dimensional space and a point outside it, I want to find an algorithm which finds the nearest point or some other point on the body to that following point. So this is a very fundamental primitive in optimization, especially constraint optimization. So this talk is going to be about the marriage of these two things. So what are submodular functions? So they are set functions. So given a universe of some n elements, it prescribes a value to subsets of this universe. And I'm going to assume that these values are integers. Not necessarily positive integers, just integers. And what makes a set function submodular is this decreasing marginal property, which says the following. Like I take a subset and an element not in the subset. So the increase in the function value when I add that element goes down as the set of the subset grows. So it's a mouthful. So the way I like it best is how my 7th grade economics teacher taught me. If you have no mangoes, then a single mango is really good. I really want it. If I have 2 mangoes, then the 3rd mango is, well, not that great. If I have 5 mangoes already, the 6th mango will give me diarrhea. So I really don't want it. So that's what submodularity is. It's as you have more, the marginal utility for next item goes down. So an illustrative thing to keep in mind is the following submodular function. So given a set S, the value is just a convex function on the size of the set. So that let's see. So this marginal utility just corresponds to decreasing derivatives. Okay, so that's an abstract definition, but I want to say that submodular functions are everywhere, and I would bet that you guys have, every one of you have seen one of it. So for instance, if I take a graph and my universe is a set of vertices, and the function is given a subset of vertices, look at the number of edges crossing it. That function is submodular. If a universe is a set of edges, and I ask, well, what's the largest number of edges that form an acyclic component? That's a submodular function. But they come up in various guises. So for instance, if my universe is a collection of random variables, and given a subset, I ask the function value is the entropy of those random variables. That's a submodular function. If I have a matrix, which is positive semi-definite, and the universe are so it's an n by n matrix, and the rows are the universe, and given a subset S, I look at the principal submatrix, take its determinant, take its log. That's a submodular function. So they appear in many guises, and an exercise for you guys would be in your research, figure out one submodular function that you've come across. The function is the number of edges crossing the cut. So in this thing, there are, I guess, 5 edges crossing this blue set. So that's a submodular function. As you have more vertices, the extra cut value increased by a vertex outside goes down. So since it appears in many forms, this submodular function has had applications in economics, operations research, algorithms, and more recently, there's a lot of work on submodularity and machine learning because they come up in clustering, variable selection, experimental design, and so on and so forth. So it's a very important primitive, and understanding them is like a key thing to do. Yes. Yes. No, so the property is the following. So I take a subset of vertices, and I look at a vertex outside it. So when I add that vertex, I look at the difference in the cut function. That difference should go down as I have more and more vertices. So, I'm sorry? Yes. Mm-hmm.
Yeah, so bigger means supersets.
Supersets.
Not just the size. The bigger set has to contain the smaller.
So here's the way to think about it. So when I add a new vertex, the cut can increase by how much? Well, at most the neighbors of these vertices, right? So when I add, say, this vertex, these are the edges that it can increase by. But some of those edges might already be there in the cut.
Except that new vertex has all its edges to nodes that you've still not looked at.
Exactly. So but then if I take a smaller set, the thing will still be outside, a subset. So let me just give an example, right? So look at if I add this vertex to this blue set, these edges are already in the cut. So the increase in the cut value will be these two edges.
Yeah, but if that vertex had a million edges going out to nodes that you've still not looked at so far.
Correct. So that will be whatever that million is.
Value has gone up by million.
Yes, it will go up a million.
So it's not, your property is not coming back.
No. But so this difference grows when S. So if T is a subset of S, this is a larger difference. So think of it as a marginal increase. When I take a new vertex, how much does the cut function increase by? That marginal increase is going to be bigger for smaller sets. If I had nothing, then I will have a million extra edges. If I had everything, then maybe all my edges are already covered. Okay, maybe we can talk offline, but this is not deep. It's just I'm not able to explain it properly.
Can I restate it? Because I misunderstood that I was fixed by that definition. So it's not the marginal difference always decreasing. It's if you have two sets, a subset and the superset. You're adding one element to both of those sets. The bigger superset is a smaller difference.
Oh.
When you're right.
Yeah, so you're not I also got confused. You're not comparing the number of edges before and after the addition.
Exactly.
You are comparing the number of edges after adding a smaller set and a larger set.
Yeah.
When you start with the smaller set and you start with the larger set, and in both
I
cases you
get
add.
that.
I had the same confusion too.
So maybe quickly,
Can't do that.
one way to think about it is a certain number of people in this room. We take the number of people outside that we one of us knows, right? That number will not increase as much if I add somebody to a larger room than if I added somebody. I think I've misunderstood the
Okay, sorry about that. Okay. Okay. So what's the problem that I'm going to look at? I'm going to look at this the following optimization problem. So I have this function given to me as an oracle. So I take a subset and it tells me the value. So there are 2 to the n possibilities, and I want to find the set which has the minimum function value. And the amazing thing is that this can actually be solved in polynomial time, polynomial in n. Although there are 2 to the n different subsets, I can do this in polynomial time. And the property that helps is obviously submodularity. And this has been an object of study for decades. And I would like to point out, so it was started by Jack Edmonds in 70s. But the first polynomial time algorithm was given in 81. And it was basically an algorithm which showed that the problem is in py using something called the ellipsoid method. It was not, you cannot say it is a true to good algorithm. And the people were trying to hunt after this of a real algorithm which they can code up, which gives you the minimum. And in 85, Cunningham gave an algorithm in the true sense of the word, but it ran in pseudo-polynomial time. So what does pseudo-polynomial mean? So it's polynomial in n, the number of elements, and the value of the submodular function. So if capital F is suppose the largest value of the submodular function, then it runs polynomial in capital F. Note that a true polynomial algorithm would run polynomial in log f, which is the size required to represent f. But this was pseudo-polynomial. And then later on, around 15 years later, this was made a polynomial time algorithm, and this was a big deal. So these people won the Fulkerson Award for this. And then it was made strongly polynomial, which means the function's value was not dependent. And this is the current record. So in 2006, Alden gave an algorithm which runs in time n to the 6 plus n to the 5 EO, where EO is the evaluation oracle time, the time that you require, the oracle requires to return the function value. So you can think of EO as 1 for this talk. So it's n to the 6, which is rather large. And what I'm going to talk about in this today is actually some work that was done in 1984. So it's a heuristic. It was a heuristic by Fujishige and Wolfe. And this heuristic, as I will show later, actually works well in practice. And in some sense, it beats this bound. But it was not known how good it is. In fact, the best upper bound on this algorithm that was known was 2 to the n square. So really bad. So basically what we did is show that, well, it's not that high. We showed that this heuristic also runs in pseudo-polynomial time. It's not polynomial yet, but it's pseudo-polynomial. And sort of this is the bound. So there's an extra f square where f is the maximum value of, well, a singleton on the function. So that's what I'm going to talk about next. So any questions till now? There is really for this heuristic or in general?
You can't construct some weird submodular function where it takes one.
So what is known is there are. So what is long? So there are experimental. So people have constructed submodular functions and done experimental. They've plotted graphs and said it probably takes somewhere between n to the cube to n to the 4 time, but it's just by graph plotting. So there is no proof that it takes at least that much time. I don't know of any lower bounds. So I'll describe the algorithm as it's a challenging algorithm to sort of analyze. Any other questions? So one question that you should be asking is, obviously there was not a 4-legged animal proving these things, but this is why Philip Wolfe, and it's extremely hard to find his photograph. Ravi, do you know who Philip Wolfe is? He was at IBM for 30 years. So as you can see, I spent most of the time in the slides trying to cull pictures of people. And Google didn't return me Wolfe's picture. But Facebook did. He's on Facebook. And I think it's him. He was in IBM. And I, friended him. But I have not heard back. He's 87 years old. So we'll see. Okay, so let's get into the brass tacks. So one object which is going to sort of be is key for why these algorithms run in polynomial time is this geometric thing called the base polytope. So what is it? So it lies in n dimensions. So there is x1 to xn such that it satisfies lots of linear inequalities. So it says for any set S of the elements, the sum of xi's on that set should be at most the value of the submodular function. So for any set, I get a sort of a half space, and this polytope is the intersection of these half spaces. And there is one extra equality constraint, so one hyperplane, which says that the sum of all these numbers should be equal to the function value at the whole set. So it's some geometric object with 2 to the n constraints. It's really ugly looking. So this is a picture due to Nick Harvey in 3 dimensions, I guess. So it's really ugly. So why is it nice? Because it has this fascinating property that if you want to actually minimize or maximize a linear function over this 2 to the n faceted polytope, then you can do that in almost linear time. So for instance, if I have C1, C2, Cn as a vector, and I want to minimize summation Ci xi, then the algorithm is just this. Sort them, set x1 to function value at 1, x2 to this thing, and so on and so forth. This is not important what these are, but this is the optimal value. So it runs in just sort time plus I have to do these many function calls. So really fast. So if EO is 1, it's like linear time. So I can optimize over this polytope in linear time. Okay. How does this deal with submodular function minimization? Why is this polytope important for minimizing the submodular function? I can minimize a linear function over this weird polytope. How do I find the minimum value of f? Well, here's a sort of remarkable theorem. So this is due to Fujishige. He said the following. So this is my base polytope. It lies in some dimension. I'm going to draw in 2 dimensions always. This is the origin. and I look at the point on the base polytope which has the minimum Euclidean norm. So this is the min norm point x star. So this is some point. It has some negative entries, some positive entries. You just look at the sort of the coordinates which have the negative entry. So that's a set of elements. That is a minimizer of the submodular function. So it converts a completely combinatorial problem into a problem in geometry. Now I have to find the minimum norm point in this rather weird polytope, but once I find it, I just read out the set. So in some sense, this boils sort of reduces submodular function minimization to finding a minimum norm point on a polytope, projecting the origin to the polytope. And I'm going to change gears now and talk about Wolfe's algorithm to find the minimum norm point. Yeah.
So do you have any intuition why that theorem is true?
Yeah, I have a lot of intuition, but I'm not going to give it now.
Okay.
But yeah, I have a lot of intuition. So we proved something stronger than we had to generalize this. We'll come to that, but I'm not going to talk about that.
Give me one big point.
Sure.
If f happens to be non-negative, which is the trivial case, then x equals 0, you can prove it comes that case.
Yes, because sorry, if f is non-negative,
Non-negative everywhere.
right, then 0 may not be in the polytope, but it all lies in the positive orthant. So
If it's a
so
polytope, that's the best solution.
yeah, but even if it is not in the polytope, the whole thing lies in the positive orthant. So the minimum norm point have all coordinates positive. So I'll not pick anything.
So it's empty.
So it's an empty set. But
Makes sense.
which makes sense,
Yeah.
but I'm not sure it gives much intuition. All points satisfy that, not just the minimum norm point. Okay, so so now I'm going to change gears, not talk about submodular functions for a while, and talk about the following problem. Given a polytope, I want to find the min norm point. So it's minimizing a quadratic function over a polytope, and it's not an easy problem. Although it comes up when you're doing projected constraint gradient descent, you have to project onto your convex set, but it's actually quite a non-trivial problem. So what is Wolfe's algorithm building on? It's basically using the fact that suppose I could solve linear optimization on a polytope very fast, which is true in the base polytope. I can do it in almost linear time. So I'm going to use that as a primitive to solve this projection problem. Okay, so first some intuition. So what do we have to do? We have this polytope. This is the origin, and I want to find the minimum norm point in convex hull of these vertices. That's a hard problem. So we're going to look at an easier problem. So this problem is easy. Suppose I give you a set of points, and if this is in n dimensions, this number of points is say less than n. And I look at the affine hull of these points. So what is an affine hull? It's sort of a translated subspace, minimum translated subspace, which contains all these points. So if there are 2 points, it's the line containing them. If there are 3 points, it's the plane containing them, and so on. So finding the minimum norm point in the affine space is actually easy. Easy in the sense that it can be done by matrix inversion. And now here's the observation, really simple observation, that if I look at the minimum norm point x star, then this x star actually lies in the convex hull of some points, so in this case just 2, such that this x star is not only the minimum norm point in this convex hull, it's the minimum norm point in the whole affine hull. So in this sort of, it should be intuitively clear in this two-dimensional picture, this point, this line is perpendicular to this line, so it's like the minimum norm point in the whole of this line. But this holds for any dimension. So that's going to be, that's the intuition. So motivated by this, let me give a definition by Wolfe. So he defines something called
So why does it lie in a convex hull?
So any point lies in a convex hull of some points. Sorry, x star lies in a convex hull of at most n plus 1 points. In fact, if it's minimum norm, it will lie in at most n points.
It lies in the affine hull.
Now, every point lies in the convex hull of some vertices, right? It's in the x star is in the polytope.
Every point is a polytope.
Yeah, x star is the minimum norm point in the polytope, and it lies in the convex hull of some points, not all points, but some points, so that it's not only the minimizing the convex hull, it's minimizing the affine hull.
But you're assuming minimum is affine. I mean, that's not always. Doesn't follow.
No. So I can always express x star. I can always find a set S. So that x star is in the convex hull of S, and it is the minimizer in the affine hull. There exists a set S of these vertices.
Affine hull of S.
Yes, affine hull of S. So for instance, okay, it's in 2D, it's only a convex combination of these points, but if I have a point in the middle, I can express a convex combination of many points, but it will not be the affine minimizer of all these points. But there exists a set S, so that it's also a minimizer in the affine hull. And affine hull minimization is easy. So Wolfe defines this concept called a choral. He says a set of points S is a choral if you look at the affine hull, look at the minimum norm point in the affine hull, that actually lies in the convex hull of this set S. So it lies inside the simplex formed by this set S. So that's called a choral. And what is he trying to find? So the algorithm will try to find these chorals, because on chorals, when I do affine minimization, I know it's in the convex hull, and it will hope that I find a choral which separates, so the affine hull, or sort of the hyperplane separating that, and the origin separates the polytope on the other side. So in pictures, it's trying to find this affine hull which separates the origin and the polytope. That will be a proof that it's the minimum norm point. Okay? So this is what Wolfe is trying to find, the choral. Ravi, you seem disturbed.
Is it not just a facet? Only
Yeah, so it is a facet, but it is also the perpendicular. It's also the affine hull. The x star is minimizer of the affine hull, and it's a facet.
So it's just a facet containing the closest point x star.
Correct. Yes. And it also is the minimum norm point in the whole affine hull of that facet.
The affine minimizer will not be the convex.
But if you find the facet.
Yes. So that's what he calls. Yes. So why he does not call it a facet? Because he's not going to work over facets. He's going to work over general set of points for which only property he needs as the affine minimizer lies in the convex hull. Okay, so let me sort of give a cartoon of this algorithm. So here's the polytope. If you remember, this is the minimum norm point somewhere here. So how does he start? He starts off with a general point A. He puts it in the set S. So this is a trivial choral because, what is the affine hull of A? It's A. Its convex hull of A is A. So that's only one point. So this is the minimizer. So it's a choral. So it checks if the hyperplane that is perpendicular to A separates the polytope from the origin. It doesn't. So it moves to, it tries to find a point here. Next thing will be try to find a point here. So how will it find that? Well, it will just minimize A transpose X over this polytope to find this point B. That's one way of finding it. Okay? So when it finds this B, so this is the linear optimization he solves here. Then he adds B to S. So this is the new green set is S. And it checks if this new set S is a choral. So what do I need to check? I need to look at the affine hull, which is this line. Look at the minimum norm point. Does it lie in the convex hull? In this case, it does. If it does, this is my new X. So this was original X, this is my new X. And I repeat. So what does repeat mean? I check if this separates origin from the body, doesn't. I optimize, I find the point, this time it is C, which is the linear optimization with X. So this is the new green point, and I add C to S. So at this point of time, I need to check if these 3 points form a choral. So this is the convex hull, this triangle. And in 2D, what is the affine hull of 3 points? It's the whole plane. So the minimum norm point is actually the origin over the whole plane. This is the minimum norm point. So in this case, it's not a choral because the minimum norm point, the origin, lies outside this triangle in this example. So it has to do something non-trivial when S is not a choral. So this is what he does. He says, this is my original point. This is my new F min, the minimizer. I join this line and see where it intersects the convex hull. So it intersects here, and that is going to be my new point. It's a little bizarre, but that's what he does. What does he gain by doing that? Since this point lies in the boundary of this hull, out of these 3 points, I can remove one point. One point is not necessary to describe this point anymore. So in particular, in this case, A will vanish. So it removes a point A from the set S. So when I don't get, when S is not a choral, I'm decreasing the size of S. When S is a choral, I'm going to increase the size of S. And then I repeat. So what does a repeat mean? This is my new S. I check the affine minimizer. In this case, it's going to be in the convex hull. I move the point, and now it's a choral. So I do the linear optimization. So in 2 more steps, basically, I'll be at the minimum hull. So this is just the pseudo code. Basically, it has 2 loops. So one is called the major loop, when it finds a choral and does a linear optimization, and that's this cycle. And then there is a minor loop. When it's not a choral, it tries to do something which sounds a little weird till S becomes a choral. So in a major cycle, the size of the choral increases. In a minor cycle, the size of the choral decreases. So if you think about it, if you look at the size of the choral as a potential, that's sort of oscillating. And that's sort of the problematic reason why this is a little hard to analyze. How much time does it take, this algorithm? Well, in each iteration, which is either a major cycle or a minor cycle, this is an expensive step to find the minimum norm point in the affine hull. It's polynomial time, but it requires matrix inversion. So let's think of this as n cube. And then it has to solve this linear optimization problem every time. But in the base polytope case, that's linear time. But these are the 2 expensive steps in each iteration. So now really what you want to understand is how many iterations does it take to go from here to the minimum point. Yeah.
So the relevant points I can understand in the picture it is a set, it's a point C. But in general, what are the points?
So I am at a point X and I'm moving to the point Y, which is not in the convex hull. Okay, so sorry, the question was how do we decide which points to remove? Yes, in general. So let me just in picture it was A. So you are at a point which is in the convex hull and you're going to a point which is not in the convex hull. As you move, one of the coordinates required to describe will become 0. So Y has something which is negative because it's not in the convex hull. X has all positive. When I'm moving, one of the coordinates will become 0. Those are the things I'll remove. Does that make sense? X is described as a convex combination. Y is also a linear affine combination. And when I'm moving,
The points that are not needed to express X.
yes, exactly.
And we break ties by doing it slowly.
Actually, I don't break ties. I remove all of them that become 0. The more I remove, the better, but because more progress in moving. Okay, so those details I'm always maintaining a convex combination, and if you think about it, that's determined. There's no arbitrariness there. Okay, so as I said, the number of iterations is key. So how many iterations does it take? So what is not too hard is that the norm of this point X, as it's moving here, strictly decreases. Okay, it's not too hard to show that. So, but what does that mean? It means that the same choral can never repeat. Again, a choral is a set of points so that the affine minimizer lies in the convex hull. Why? Because when I find a choral, the point is the affine minimizer, and since the norm is strictly decreasing, the same choral cannot repeat. How many chorals are there? Well, there are some v number of vertices. There are n. We choose n ways of choosing it, so that's v to the n. So the number of iterations at most the number of chorals, which gives you this n v to the n, where v is the number of vertices of the polytope. So if v is like, number of vertices could be exponential in n, so this gives like 2 to the n square. So Wolfe, this analysis is due to Wolfe in 76, and here's what he says. He says it's a calculable number, but the result is preposterously large. As with linear programming, we must resort to experiments to determine whether the method is practical. And then he basically takes some random polytopes. I'm putting another quotes because what is a random polytope? So, but what he sees is that if n is the dimension and m is the number of points, the vertices, and it grows really slowly for a random polytope. And he has a bunch of these experiments, and he says, it's a very interesting paper, by the way. He says that it should be logarithmic in the number of vertices rather than exponential. So that's his gut feeling. He says something like that. Okay, that's for a random polytope. This is way back in 76. And then I think it sort of died down, as in no one, I don't know of many citations of this. Till there's a paper written by Fujishige and Isotani in 2009, who basically revived thinking about whether this Fujishige-Wolfe, which is just applying min-norm on the base polytope, can be a practical algorithm. And they did an experimental paper, and this is a log-log plot. This is the Fujishige-Wolfe algorithm, and these are all the provable algorithms, that run in polynomial time. So this experiment suggests, again, this is on some benchmark data, but it suggests that maybe you can actually prove that it's polynomial time. So what do we prove? We prove that for any polytope, in not too many iterations, so n q square by epsilon square iterations, I get to a point whose norm is within epsilon, additive epsilon of the min norm, and q is actually the max norm point in the polytope. This can be rather large. It's a little irritating. I think this can be replaced by the diameter, but I don't really know how to do it. But that's what we prove about Wolfe's algorithm for any polytope. So basically, if you think of q as some sort of a not too large constant, then in linear number of iterations, I get epsilon square close in min norm. Okay, but how does it help in submodular function minimization? Because Fujishige's theorem, which said that if I go to the min norm and read out the negative entries, that seemed like a very delicate quantity. But it's not. So there is a robust version of Fujishige. So we have a proof, but this has been sort of noticed by other people, that in fact, if you have a point in the base polytope, which is not the minimum norm, but it satisfies sort of this technical constraint for all q, then I can find a set S which is very close to the minimum. So f of S is actually at most the minimum plus some 2n epsilon. So it's sort of a robust version. I don't need exactly the minimum norm. If I'm approximately minimum norm, I can find approximate minimizers. And now if I have an integer value, then I can set epsilon to be anything less than 1 by 2n, then this will be the minimizer. So you can do that, and then you get basically combine these two and get this pseudo-polynomial time analysis. Okay? So I'm not going to talk about robust Fujishige. But I'm going to spend some time on this analysis. So any questions? Yeah. Yes. So q. So the max norm in the submodal polytope is nf square. Okay. A sketch. So why does this algorithm work? Okay. So there are major cycles which increases the size of coral, minor cycles which decreases the size of coral, can go all over the place. But let's assume, so let's take a major cycle where there are no minor cycles. So what does it mean? I mean this was a coral, and then the next step, again I get a coral. So I don't do this minor cycle again. So in that case, one can actually argue that the norm significantly decreases. So basically this was my old point, this is my new point, and x old, x new, and q old, which is the sort of the linear optimizer, they lie on the same affine space. So you can do some sort of Pythagorean theorem and get that the norm decreases by something which is large. So this is just the dot product. So this is just saying that this square minus this square is just the dot product here. This is not something deep, except for this inequality. Now why is this large? Well, if this were small, then I will terminate and go home, because I found a point which is already epsilon close. So this is at least epsilon square. So I should not do this. So this is my stopping condition. So I have not stopped. So this quantity is large. So I am making some progress. So if I had no minor cycles ever, then I will, in the reciprocal of this, I'll be done. But of course, that's stupid, because if I never have minor cycles, then in n iterations, I'll have n points, or n plus 1 iterations, I have n plus 1 points in S, and then the affine minimizer is 0. And unless 0 is in the polytope, I will do a minor cycle. So minor cycles are the challenge. So why is it a challenge? So here's a minor cycle. So this was a triangle, that was my S. The affine minimizer was Y, and my X nu was on this line. The problem is that the previous slide showed that Y's norm, in this case 0, is way smaller than the X old's norm. But X nu can be very close to X old, and you don't get anything. Okay, so then you can say, well, just do your minor cycles, there will be not too many of them, and next time you get a coral, you try to argue that you get a big drop. Again, that is a problem, because you run, say, 17 minor cycles, then you at some point X current and X nu, so you'll get something which was like in the previous slide, but this expression, I cannot again say it's big, because this Q was a linear optimizer at some other point. It could be 0 for all I know. So the challenge in Wolfe's algorithm, I think, the reason why it was still unanalyzed was this minor cycles cause a big headache. So how do we get about it? It's a little of a trick. It's not a very, I don't think it's the final word yet. So what we do is this. So we know that if in a major cycle there are no minor cycles, I have good drop. We show basically that if there is at most one minor cycle also, I have big drop. Why is that? So what does that even mean? So I do, this is as in the picture, I go to the affine minimizer, I go to this new point, and now when I throw away one extra point from S, this becomes a coral. So these are two coral things. So why is this good? Well, what do I know? I know that X old and Y are far apart in norm, because Y was the affine minimizer, so it's large. Think of this as large. So if Z was very close to Y, then I'm done, because just by some sort of averaging argument. So if Z is far away from this X old and very close to Y, I'm done. So I may assume Z is very, very close to X old. But now this new X nu is also an affine minimizer on this point, on this affine hull. So I can again apply the old theorem and prove that the difference between Z's norm and X nu's norm is rather large, where large depends on Z and Q old. So I am getting technical here, but the point is if you squint and say, well, Z is very close to X old, so it will behave like X old, then I know that this quantity is large. So basically in summary, if I have only one minor cycle, I still can prove that the drop is at least epsilon square by some 8q square. So I went a little fast here, but sort of trying to give a flavor of what kind of proof is. The proof breaks down if I have more than 2 minor cycles. I don't think it's an inherent thing, but one should be able to prove more. Okay, so in sum, what did we show? So we have these minor cycles, major cycles, major cycles, minor cycles, and if there's a major cycle with at most one minor cycle, norm significantly decreases. But what if this never happens? Well, here's a very simple but crucial fact, that minor cycles are increasing size of S, major cycles are decreasing size of S by 1. So if you have this major, major, minor, minor, major, major, minor, minor, this cannot happen for long without having one major cycle with at most one minor cycle in this. So if you just plus 1, minus 1, plus 1, minus 1, the string of them, and if the running sum cannot increase more than n or decrease more than 0, then somewhere there will be either 2 pluses with at most 1 minus in them. Just a simple fact. So what it shows is that in 3n iterations, I will have significant drop. So I have an extra n factor here, and that's basically the proof. So it's really a cheeky fact, if you ask me. I think this n should be removable. Okay, so I'll end here with some takeaway points. So Wolfe's algorithm is actually quite an interesting algorithm which works well in practice for finding the minimum norm points of polytopes. I don't think there has been as much experimental work done on it as should. There are some new works that they are doing it, but mostly for submodular functions. But you can ask it for any polytope. So a concrete thing is, well, can you actually prove that on submodular polytopes runs in polynomial time? Not f square, not even log f. So we did the following experiment. We took the graph, the line graph, and we look at the min cut on the line graph and increase the capacities. So as you increase the capacities, the function value increases, capital F increases. and we plotted Wolf's number of iterations. Does it increase with f at all? It doesn't. It just stays flat. While so it seems to suggest that it might be actually polynomial time, and that will be a really cool result. And more bravely, prove that Wolf's algorithm runs in polynomial time for all polytopes. That will be super fascinating. I'm not sure I believe that, but there is no disproof of that. And so with that, I'll end. I have a slide. How do I make it visible? So, just to name clustering, variable detection. Okay, so here's one. So suppose you want to cluster points, and the points are actually random variables. And you have to break it into 2 points. How do you do it? There's no, agreed upon way of doing it. One way is this thing called minimum description length. So they're random variables. I want to cluster them, and I say, well, to describe this whole ensemble, what's the minimum number of bits you need? So what this animation was trying to show is that if these are the random points, and actually this class is just a scaling of these random variables. So once you specify the left, the right is deterministically specified. That is some sort of a good clustering. So if you stare at it, it basically is trying to find a partition of these random variables which minimizes what is called the mutual information between them, which is a submodular function. So this was actually, I'm not inventing them. This was a paper by Narasimhan et al. But more interestingly, here's a new thing that's quite fascinating. So this is a kind of problem that machine learning people want to solve. So it's least square with a regularizer term. And what is a regularizer trying to do? So one property might be you want to sparsify the optimum value. So there's this thing called structured sparsity, which is trying to say, well, you would like the support to have some more properties, some minimize some, not just the cardinality, but say minimize a submodular function. And this has applications in variable selection, experimental design, and so on and so forth. And what was showed is that, so without going into the details, if you want to minimize this, it reduces to minimizing some translate of a submodular function, which is also submodular. So you can use these algorithms to solve that. In fact, they use the minimum norm point algorithm. So there's a lot of experimental results trying to do this. So this has, again, this itself has a lot of applications in various areas of machine learning. So semi-supervised learning, unsupervised learning, and so on. I must say I'm not an expert on understanding the applications, but it does have, and they're really excited.
So are these different algorithms than the ones that you currently use while minimizing?
So for this one, the main thing is that this way of this regularizer, if I have a general submodular function, no one has looked at it. But you could use it. So you could use, I showed you this submodular function arising from matrices. So that is used for doing some sort of variable selection, Bayesian variable selection. So there are papers written. Now whether they are used in practice, I think it's too early to say. These are all quite recent, but they may be. And they're decently fast. And in fact, they do the min-norm point algorithm or some other variation of that. Yes.
So how does this compare experimentally to other heuristics for Euclidean projection onto general polytopes?
So what are the other heuristics?
I don't know. I'm asking.
I also don't know. I know of Wolfe, and I know of Frank Wolfe, which was 15 years earlier by Wolfe himself. So the difference between Wolfe and Frank Wolfe is that Wolfe is maintaining a simplex, which grows, and Frank Wolfe always maintains a doubleton. How does it compare experimentally? I don't think anyone has done a rigorous experiment. We have done some, and Frank Wolfe also gives a pseudo-polynomial time guarantee, but it is actually pseudo-polynomial. So in this example where there is this line graph with increasing capacities, Frank Wolfe iterations grow with f. Wolfe doesn't. So, but I think that's an excellent question. As in, what are the other heuristics for projecting on a general polytope? I don't think it's seen that much work yet. This is really cool. Wolf's algorithm is really cool. So I can ask a question. So how many of you had not seen submodular functions before this? Okay. How many of you think that if you think about it now, you can find a submodular function? If I do a better job in explaining what they are, but so Monojit already has. No, they are everywhere. I just did a bad job of explaining what submodular functions are, but they are very as basic as convex functions, one might say, the discrete analogues of convex functions. Okay. Thanks.